Hi there, here's a little problem I've been sent. I got sent an HCalendar text file, so I wonder what that is. So let's have a look at this text file. Open with Notepad++, that's what I use for these things. No, I don't want to update this, and I will resize this to see what's going on. Okay, so this is just an ins file with nothing in it, and this is a charge flipping instruction from Olex2. So what it is, it's an ins file. So all we need to do is rename the text to ins. The reason why this was named as a text file is that if you're trying to send an ins file through email, it will probably get rejected. So there's no need to go into any other software, you just rename it into ins and there we go. Alternatively, you could send a res file and it will just send fine. So we're dragging this into Olex2 and we see what we get. We shouldn't get anything because there's nothing solved yet. So we've got a tentative formula, we've got very good data, we've got a cell, so that looks great. So let's solve it. Olex2 solve, we can try superflip or Olex2 solve. Let's stick with Olex2 solve for the moment, and we hit solve. And that will take a little bit of time to run, and here's the output. What you're looking for is this number, which should become bigger and bigger and bigger. And if it doesn't, this particular program will not solve it, but it has solved it. So there we go. We see the Q peaks. So these are the electron density maxima we've got in our structure. If I click on this Q again, I can see some bonds. Now that doesn't look like a very promising solution. And we know there's possibly magnesium in there. So what we'll try to do is just to select these heavier things as magnesium, and we go name MG. And just refine it and see what we get. So this looks not bad. So we actually got some atoms here and some connectivity. So these ones are probably oxygens if that's magnesium. We select these oxygens here, we select these atoms, and then we make them oxygen. Alternatively, we can pick the oxygen and then click on that and make them oxygen that way, or we just keep going here. Now we've got some atoms in here, we hit escape or click the escape button here and refine. Notice it doesn't really matter that we've missed some out, they'll come out in the wash as it was. So that looks interesting. So we're going in here, we're making these ones more oxygens. This one's probably a carbon if that's the case. So we have a carboxylate, a formate possibly. But what is very strange here is that these magnesium are quite small and these oxygens are quite large. So let's see what's going on here. So we look at that. So something is wrong here. So that really does look like a formate, and this is a metal with 5 or possibly 6 atoms around it. So that looks quite plausible. Let's click on this and put everything together. So now we have the slightly better picture here. So there clearly is another carbon in here. Right, but something isn't right. So these magnesiums can't be magnesiums. They must be heavier than what we're seeing at the moment. So let's hover the mouse and see what it could be. So that's 2.1. Now that looks a perfect first row sort of transition element sort of thing. So let's try and make them, I don't know, let's try copper. So we go name CU and refine that. The R factor is 24%. And if we refine that, let's see what we get. Oh, that looks a lot better. The R factor, 22%, not great, but things are starting to look a bit better. Now this one we've forgotten, so let's make this a copper as well and refine this. So at least all these spheres are now roughly on the same sort of scale, so that's more promising. Any Q peaks that we haven't looked at, just pressed Ctrl Q, so that toggles these Q peaks. So the biggest peak is 5.5, so let's make it name C and hit refine again. And instead of hitting refine, you can also just type refine. So let's make this a carbon here. So name C, Ctrl R, refines without doing anything more. And now that's all coming together. There's a carbon here. Oops. And that's almost certainly another carbon. And the R factor is now dropping nicely. We refine again. put everything together. So now it looks like we found all the non-hydrogen atoms. Now these are all isotropic, so they're just balls. If you make them into ellipsoids, we click on this thing here, it makes it into ellipsoids. Because this is ticked, it refines automatically, and we get an R factor of 7%, so that's fairly good. Now I'm not convinced that these are actually copper because they look too big. So we can look at the electron density map, and yes, it does confirm it. There is too much electron density assigned here. So let's try for something obvious, maybe iron. So we go name Fe, and we refine this again, and 5.84%. So this is looking fairly promising. Let's look at the map again. Of course, we've got absolutely no way of knowing what this is. So we've been told there was magnesium. There clearly is no magnesium here. It could be copper, it could be iron. So without the chemistry and knowing what's happening here, we just simply cannot make any decisions here. So the biggest peak is 0.4. So that's excellent. It's very small. So we add hydrogens to this automatically, and see what we get. So this thing is more or less done. So what we now can do is, so if this oxygen sits here, but if we when Control G, we will see this grow. So if we keep growing on these bonds, so this is like a polymeric network, and it keeps going and keeps going. So if we type fuse again, we go back to the asymmetric unit, and we might want to tidy this up because this is clearly another one of those formates. Probably this one. What we can do here is go to the growing area and go mode grow and then move. And now we can see this here. If I click on this, it's going to move that atom, and it moved that atom here. So that's a carboxylate. Now this one's not complete, so we moved that oxygen here. And the last one here, so this was that one. So now what we've got is a fairly clear picture of what's going on. This asymmetric unit has got iron, and then it's bridged by these formates. Now to me that looks like it's a structure it's probably known. We need to find out this formula unit of this. So at the moment we've got Fe12. Well, that's not really very sensible, but that's because Z prime is set to 0.25. And let's just say we set it to 2 and see what we get. So this is now C3H3 Fe 1.5. That's not very useful. So we could set it to 4. Does that make any sense? Now that doesn't make any sense. What about just 1? And we have a unit of C6H6 Fe3O12. Now this is very much now a chemical decision that has to be made, what formula you would like to choose here. Anyway, there's still some shifts, so we refine this some more, and we hope that this shift will stop and settle, and has that settled. Now the completeness is 93%, but we're going out to a great 0.62 angstrom, so this is a very high resolution data set. It looks to me like it's a room temperature data set. It's a pity. It would be nice if this was low temperature. But the next step, of course, is to make sure in the CSD that this is not known, and this is actually a new compound. But other than that, I think I've shown you how to get to the structure by a standard solution, electron density assignment, and chemical knowledge put in there. I'm not saying this is necessarily iron. It could be cobalt or nickel, or we don't know what was put in there. So without that knowledge, we have to consult with the chemist what's going on. Okay, I hope this was useful. Thank you. Oh, thanks for using Olex2.